way to look at deviation from the background is, sorry, I'm already classifying them, there's three of them, is phylogenetic shadowing. Phylogenetic shadowing, you guys probably seen that or done it once. And what you do, you sort of align the two genomes against each other, and then you will look how many differences are between the two sequences in the window. So you move window across along the genomes, and you say, okay, there's a window of 100 nucleotides, and from them 50 are different. Okay? And you move to the next window, and already it's only 20 that are different. So the first window was not well conserved. The next window is a little bit more conserved. And if you look between humans and chimpanzees, obviously the conservation is on average high. And if you look at between humans and, let's say, orangutans, it's going to be a little bit more. But different places in genome will have more differences than others, right? And the places that have more differences, those places are accumulating differences at a higher rate. So they're probably not we call it not so evolutionarily conserved. So they're not accumulating these places faster. Now the places that don't have that many differences, well, that's probably because if the difference is there, it might change something. They make the gene non-functional. So evolution conserves these places, right? And these places are likely to be genes. And this type of selection we can call it purifying selection or negative selection. We're selecting against change. Okay, so here is there's a scan across many primates, and you look that in this place there's places where you accumulate many differences, and there are places where you don't accumulate any differences, and that must be something mildly important. Now, if it's a gene, we kind of know why that happens. But this kind of selection scan is often used to look for places that are conserved outside of genes, and that's how you find regulatory elements. Because regulatory elements, you don't know what this kind of sequence it would be. You just know that because there's no difference between human and gorilla and chimpanzee and a macaque, there must be something important here. So we use this kind of selection scan to look for these regulatory differences. Okay, that's easy. Obviously, there's a way to evaluate how much difference can you accumulate, etc. So you can play with the math, and as I said, I'm not going to do very much math here. The other famous way for looking for selection is looking at the rate where mutations accumulate between synonymous and non-synonymous sites. Now, if you remember what synonymous and non-synonymous sites are, most of the bioinformaticians know what that is. Most of people that are working with wet chemistry sometimes don't. So I'll just quick reminder: non-synonymous site changes amino acid. Synonymous site does not change an amino acid. So if the mutation accumulation is random, the rate between synonymous and non-synonymous sites should be about equal. If all of a sudden you start getting a lot of non-synonymous sites, which means a lot of change is accumulating, that means there is selection. And this selection is different than selection we saw before. This is what we call positive selection. Selection for change. Before that we had selection against change. This is selection for change. Okay, so what am I talking about? Let me show you an example. So and our paper has many examples like these where you can just look and see what I'm talking about. So here is your forest, and here is your lion. Okay? The difference between the patterns. If you look at this gene, and its alignment of amino acids across the gene, you will see every line means it's the same amino acid. So this gene between human and rhesus macaque looks like, there is some rate of non-synonymous mutations, right? It's about every fifth amino acid is changed. Here and here. So it's not, you don't expect many non-synonymous mutations to occur. Except there's one place where a lot of them occur. And this is an unexpected pattern. This is the pattern that you normally don't see. And you can check that by looking at other genes and trying to calculate what's the average ratio. And you can, usually what people used to do, they would just take 20 other genes and they will calculate what the ratio is. And they will take your gene that you suspect for selection and see how unusual this pattern is. And you say, okay, well, usually you do not see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 amino acids changed in a row. And that qualifies as a selection signature. Okay. Now, you can incorporate incorporate a population diversity into this reference genome comparison. So this is sort of a hybrid step. Because you might not know how much deviation to expect. And also, if selection happens, the first thing it does, selection is always for something, right? So that means if you have a diversity, you see all these apples? All I'm going to do is to pick the red ones. So all of a sudden diversity is lower because I only have the red ones. I don't have the yellow ones anymore. So the effect of selection is to reduce genetic diversity. That's the most important thing. But what if you don't have a reference point? What you don't know how much of that diversity in population you can reduce. So one of the things we can do, we can compare divergence between two species and then diversity within those species. Well, I'll show you what that means. So diversity is this. This is a population. So you have many individuals in the population, and you look at a pattern of diversity within the species. And you use to evaluate that, you use another species as a reference. So if your diversity decreases, this is the ratio that you actually calculate. So diversity here has decreased, right? But you know that because you compare this diversity to this divergence. This divergence is always the same for every gene, but in some genes, this diversity is lower, and you know that because you divide your diversity by divergence. And that is another signature of selection. So let's look at what it really looks like in a genome. Here is the genomes of two plants. Corn, kukuruza, and Hyacinthe dika, wild corn. Wild corn was about this small. It was a little tiny cob. Cob is kachata. It's very, very small. People have selected corn to be big. So the selection test was done in the gene that on the gene that was suspected to be involved in the size of the corn. So here is diversity. Diversity in two populations. This is the wild corn, green, and this is the domestic corn. So the actual gene, I don't know why it came out here, because there's actually a picture of it. Should be a picture of the gene up there. In any case, the gene starts right here. And you can see that diversity and divergence between these species are not very high anywhere. So here this whole gene has about the same pattern in wild and domestic corn. Now, this is a promoter area. In a promoter area, you have the wild corn with lots of diversity. Some wild corn has a promoter with this sequence, and some wild corn has a promoter with another sequence.
So why axis it's a kind of
yeah, there's a diversity. There's a diversity inside the wild corn.
In nucleotides.
Yes.
In
the population.
In some gene.
Before gene.
Before gene.
This promoter. The domestic corn has been selected for one type of promoter. No diversity. Why? Because this is the one that makes it grow big. So this is a signature of selection. There's a diversity in one and no diversity in the other.
But is it one gene or it's several genes?
This is one gene. So
gene.
the genes, yeah. I had a picture of a gene there.
Okay.
In a different in this. Somehow it fell off when I moved it from one slide to another. But the gene starts from here, and you can see it in. Can I? Mm-hmm. Oh, you still have those galleys. So you can see that the gene starts about here.
So it means domestic corn needs stronger promoter to make it bigger, no?
But it only has one. Among thousands of different variations of wild corn, we selected one that makes it grow big. It just makes sense. Okay? And that is the signature of selection. So you know that divergence between them is the same along the whole gene, because it's, you know, there's no difference here and here between how divergent the species are from each other. But the diversity is quite different between them two. Okay, so, and usually when we talk about this, we talked about this in this paper, we would give a summary table, and in that summary table, we will, this is the 3 signatures of selection based on reference genomes, and there is papers that will use this method, and you can click on this paper and get to the test, and it will tell you what kind of selection that you are likely to find. It will tell you also in the human populations, if you look at the human populations, what is the time scale. And most of these are done, if you want to look between humans and another species. If we believe that our species are more than 1 million years old, then it has to be looking at events that are more than 1 million years old. But as you know, people keep trying to look. You use these selection tests to look at selection that happened 10,000 years ago. What are they going to find? Nothing. Because it takes longer for these things to show up.
So hold on a minute here.
Sometimes it's a
the
population.
time frame that you should be a window. So what's the minimum and what's the maximum for DSDN? What's the minimum, the maximum for McDonald-Kreitman? What's the minimum, maximum for the divergence rate using phylogenomics shadowing?
Can I show you that slide at the end because that's a summary slide.
Sure. Okay.
We do have that
But
slide.
that's fine. But I want to know how you get that. How you get the range. How do you determine that? You come up with this gorgeous algorithm for looking for it. How do you know when it works and when it doesn't?
How do I know when it works? No, I don't know if it's not going to work. It's just
No. How do you know
not
what the time
likely.
interval is that it's applicable?
Well, it's a theoretical thing. You just think about it's sort of a theoretical exercise. You don't know that. You might be able to find a very recent one if the selection is very, very intense or something, like artificial selection in corn, because people really, really, really worked on it. But if you're looking at the wild species, these kind of changes do not accumulate very fast. And the reason I put 1 million years there is because it's looking at a different species. And between human and another species is at least 5 million years. It's human and chimpanzee. Now we can look at human and the Neanderthal, and people are looking at that. But you don't look at
Well, human and Neanderthal are 300,000 years. Do you see this kind of thing in there?
So you should probably be looking, but Neanderthal genome only been published. Well, it was published after this paper, so that's why we didn't put it there.
Right.
And now Denisovan, Denisovan is actually even older. Neanderthal is kind of hard to search. We looked at Neanderthals and terrible to line. But if you want to look at something like this between humans and Denisovans, easy, just personal experience. Nice genome.
Question, if you know, for the scope size. So they look from very small to middle and high, yes? So that means that promoter kind of changes gradually, or they just like jumping from one trait to another one? Because how it's work?
The mutation rate should be, so the pattern of the forest should be sort of the same. So mutation rate should be everywhere the same. Now, you have purifying selection changing mutation rate in the middle of the genes because you just don't accumulate mutations there in general. But then, in a promoter, again, it should be a little bit lower, but not so low. And in the case of selection, it just went to 1.
So it means there are intermediate promoter, which is
in wild.
Yeah,
in the wild.
Weak and strong promoter intermediate.
Yeah.
And
In the wild, you have all kinds of variation. Just think about it. Think about this. Think about a wolf, right? A wolf is a good example. Wolf has every type of genetic variation that we selected today to every breed of dog. Theoretically, if you cross all the dogs together, you will get a wolf, right? But each dog has only part of genetic variation of wolf, right? It's only that promoter for the big dogs, and only that one for the small dogs. But wolf always had all of this. These are new. Most of those mutations are not new. They always existed in the wild population. So wild population of corn, the same way, has everything, and then we select from it certain things to our liking.
Well, you also have to worry about the time element because often you might have some level of variation X at the time of domestication or at the time of the founder event, and then as you go on, you know, you delimit it. And meanwhile, the parent population is continuing to either grow or go down in diversity. So when you look at the modern population, it's not always identical to the parent population of the wolves and we saw this in the tigers, for example, when we discovered genetic impoverishment of wild Siberian tigers. But when we actually looked at the captive tigers, it was much bigger because they'd been in captivity and had been retained. So no matter what you do, you have this issue.
Right, and so making a correct comparison is good. So these genome studies are good because one of the things you do, instead of having one gene that you compare to another gene, you have all of a sudden access to information across the genomes, right? So you don't say, okay, how does this gene stand out? You have 20,000 of other genes to actually be a reference to the value that you got in your gene, right? So that's how you do selection scans across the genome. Okay, so as I said, the other types of and we already touched on it a little bit. The other the other way to look at the selection is look at population data, and this is just a general slide about the SNPs. Obviously, here everyone knows what they are, and so what selection does to these, so this is your wild population, right? And the selection goes through that population. This is the intermediate step, and this is the final step of selection. What it does, if it selects that chromosome with the variation on it starts increasing in frequency in the population. So here is the beginning, this is intermediate, this is sort of an end stage, which is called fixation, where this blue allele that has an adaptive value has increased to 100% in the final population. So now this population in this place only has that allele, nothing else. You also notice there are some other alleles that are sitting next to it. They are not adaptive, they're neutral, they have absolutely no value, but because they're close proximity to this allele, they will hitchhike. We call it hitchhiking. Hitchhiking is standing on the road, putting a finger up. That's hitchhiking. So these are hitchhiking alleles. They just caught a ride with the adaptive allele. Okay. Now, what else happened is that you have all this variation here, and as this chromosome increased in frequency through intermediate step, here there's absolutely no variation left. This is a complete, we also call it a complete sweep. This is what we call an intermediate sweep, a little bit more difficult. So complete sweep is easy to find usually. Intermediate sweeps are harder, and most of them are intermediate. But another thing to notice that there is another force in the genome called recombination, and if the sweep doesn't happen very fast, then other chromosomes could recombine, exchange pieces, and some of the variation will be added back into the region. So this chromosome here is now not the full chromosome, it has pieces from other chromosomes. And with time, and with migration, you keep adding more and more and more of these non-adaptive chromosomes. So even though selection keeps occurring, but the variation keeps being added and added and added to the place, and the selection region starts getting smaller and smaller and smaller because other chromosomes will add more and more variation to the flanking regions around the selecting site.
So you say chromosome does mean aneuploidization, or you mean by chromosome just locus?
So chromosome is a chromosome, and then locus is in the middle of it.
Yeah.
At first, the whole chromosome gets selected.
So it means several
In
chromosomes.
the first generation. The next generation, chromosome gets selected again. But the ends of these chromosomes already recombined with other chromosomes from other individuals with which they were produced. So when it gets selected, it's not a full chromosome, it's only the part of the chromosome, right? And that part, it may be shared among individuals which might have ends of the chromosome from somewhere else. And that region gets smaller and smaller. The region that you select on gets smaller and
I
smaller.
mean,
and
this
smaller.
one you show 100% of chromosome. Is it in one individual? You mean it's
No.
It's
This
a
is population.
Population. Okay.
So the effect is a decrease of variation inside of
In
population.
population.
Okay, the other way of thinking about this is in sort of a genealogy or coalescence. And so here is different scenarios of how selection happens in the population. Population survives in its ecological space. So it's limited in size. You can't, remember Darwin, you can't reproduce, you can't, the elephants will not take over the earth because because there is selection. So here is how, given enough time, any allele will go to fixation. Given enough time, at random, you start somewhere in time. Any allele either will disappear or become 100%. And the chance to become 100% of a fixed in population is, as you remember, it's 1 over 2n. Okay? So it's very small. The chance is very small that any of them will take over. So, but here's the scenario how it does. You would just spread in all this red. It randomly takes over a population. If there's a selective force behind it, if this allele is important, it will take a lot less time to do this. You see this? And you see this. There's also other ways of selecting. There's a balancing selection. A balancing selection is when you might have two adoptive alleles at the same time. So you have the blue and the brown. Okay.